All right, guys, so here we are. We're going to close out the year with the last couple sections, which are on spheres and similar solids. So going quickly through, just starting with the surface area of a sphere. So the surface area of a sphere actually comes out, interestingly, to exactly 4 times the area of a circle with the same radius. So the surface area is just 4 pi r squared. So if you're given a surface area, you want to find the diameter, so you can set up sort of an equation. So the surface area is 4 pi r squared. They're giving me a surface area of 20¼ pi. So if we divide both sides by 4 pi, that's going to give me r squared equals this long decimal, 0.625. And then taking the square root of both sides, remember we don't have the the negative square root because that wouldn't make sense. You can't have a negative unit length. So the radius is 2¼ centimeters, which means the answer of my question is the diameter will be double that. It is 4.5 centimeters. Okay. Now, new phraseology, new term here of a great circle. Okay, so a great circle is really this really big circle. Okay, so if you took a plane, we did cross-sectional area. I talked about that a couple of times previously in this chapter. If you take a plane and you slice into a sphere, okay, one thing that could happen is if you're just tangent to the sphere, the intersection will just be a single point. But at every other point, the intersection is a circle. Okay, no matter how you cut it, it's going to be a circle, and the circles are varying in size. The great circle is the largest circle from a cross-section. So it is basically the fattest part of the sphere for you to slice through. So it is the largest circle that's formed. All right, and the circumference of the great circle. So the circumference of the great circle is the circumference of the sphere. So when we talk about what is the circumference of a sphere, you're talking about what is its circumference at its widest point. So cutting it at its great circle cuts it into 2 half spheres. Those are hemispheres. Okay, so you'll know that terminology probably from thinking about just the globe. And so in that same context, a great circle, the great circle on a globe would be the equator. All the other latitudinal lines are smaller circles. All of the longitudinal lines go all the way around through the poles. All the longitudinal lines are also great circles. So the only one that goes horizontally that's a great circle is the equator. All of the longitudinal lines are great circles. All right. Here we go. Word problem on a sport called sphering. I don't know if the sport never took off, but it seems slightly outdated. Don't think this is much of a sport. But the person rolls down a hill inside of an inflatable ball. Okay. The circumference of the outer ball is 12 pi feet. Find the surface area. So they tell me the circumference. Circumference is 2 pi r. So if they tell me the circumference is 12 pi, then I can find out that my radius is 6 feet. So if I want to know the surface area of the outer ball, surface area is 4 pi r squared, so the surface area is 4 pi 6 squared. It's going to be 144 pi square feet, which is actually pretty big. All right. All right. So that's surface area of a sphere. Let's talk about volume. The volume surface area formula is kind of a fun one to memorize, but it's even more fun to derive. Okay? So deriving the volume formula, I think is a lot of fun. So basically what you want to do is take a sphere, okay, and if you break up its whole surface area into these little kind of square pieces, okay, so we're going to say we're going to divide the surface area into n things that are approximately squares. Okay, now they're not perfectly squares because they are on a curved surface. Okay, so what this does is it creates, okay, n things that are approximately square pyramids. Okay, so this little slice here, so you have this little piece here in green as part of the surface of the sphere, which means it actually does have a little bit of a curve, okay? But if you made it's very, very small, if you made it very, very small, that curvature would be very, very minute, okay? And so this is really a concept that's used very heavily in calculus, is the idea of kind of limits, the idea of what if I made this like arbitrarily small, where it was so small, the square was so tiny that it was indistinguishable from being a pyramid, right? The bottom part being a curve could actually be negligible if this was made sufficiently tiny, okay? But if you just picture this is fine. There's a little bit of a curve here, so we'll do this as an approximation. So then the volume of the sphere is going to be the volume of each of the little pyramids times however many of the pyramids you are, right? It's a pyramid because you have the radii of the sphere going down there. So the radius of the sphere is like the height of the pyramid, okay? So if you remember from the last section, the volume of a pyramid is 1/3 area of the base times the height, okay? Now in this case, the height is the radius of the sphere. So I'm going to just kind of move some stuff around. So I'm going to do, this is 1/3 n times b, and then h is just r. It's just the radius of the sphere. And now this part, this is where kind of the fun happens, which is that capital B is just the green area here, okay? And I have n of them. And so when I have all of the bases combined, that makes up the whole surface area of the sphere. And we just talked about this, where the surface area of the sphere is 4 pi r squared. That means that my volume formula is 4/3 pi r cubed. So that is the volume of a sphere. So to find the volume of this composite solid, this is like a cylinder with kind of a bowl cut out of it. So I like to write the sum or difference of the pieces when I have a composite solid. So I'm just going to write, for my volume, it's cylinder minus hemisphere. Okay, minus half of a sphere. And so for the cylinder, cylinder is the area of the base, which is pi r squared, times the height, which is 2, minus the hemisphere is half of 4/3 pi r cubed. Okay, so hemisphere is just half of the volume of a sphere. So my volume here, this is 2/4, is 8 pi. And this is 16/3 pi. So the volume here ends up being positive 8/3 pi cubic inches. Okay. Similar solids. We've talked about kind of similar shapes before. Okay, two-dimensional shapes. Remember, they're similar shapes if they have equivalent ratios for their measurements. Same idea here for solids. First, they are the same shape, meaning you're comparing a triangular pyramid to a triangular pyramid, a hexagonal prism to a hexagonal prism, a sphere to a sphere. So they're the same shape. And then the ratios of each linear measurement are equal. Now, the linear measurements are things like radius, height, length, width, etc. Okay, so any one-dimensional unit that you'd be using to measure the shape, all of those ratios have to be the same. Okay, so here these cylinders would be similar. Okay, so the ratio of the radii would be equal to the ratio of the height. So radius and height are the only two measurements for cylinder. Here, these cylinders are not similar, okay, because the radii are not the same and the heights are. So the ratio of the radii is not the same as the ratio of the heights. Okay, so if the heights were to be equal, then the radii would also have to be equal for those to be similar. In that case, they would be congruent, actually, as well. All right? So, tell whether the solids are similar, explain your reasoning. So we're checking two things. One, are they the same shape? So this thing here, yes, these are both rectangular prisms. Okay? And then the other part would be to check the ratio of all the linear measurements, so the length, the width, and the height. So the ratio of the widths is 2 to 9. The ratio of the lengths is 16 to 12. The ratio of the heights are 4 to 3. So these are reduced by a factor of 3. These are reduced by a factor of 4. These things are all the same. So this one is yes. So they are the same shape, and all of the linear measurements have the same ratio. Okay? Now here, these are both right triangular prisms. Okay, so these are the same shape, right? Now their corresponding measurements here are 3 to 1.8, 4.5 to 2.7, and 2 to 1.2. Okay? So this reduces to 5 over 3. This reduces to 5 over 3. This reduces to 5 over 3. So these are all the same as well. So these are also similar. Okay? These reductions, by the way, you don't need a calculator to do these like reductions. You can still do these without a calculator. Just as a little mental math note, when you're trying to reduce fractions that have decimals, just kind of move you can do this on paper. You don't have to do it in your head. If you scale this up to no longer have decimals, if I multiply these things by 10, instead of it being 2 over 1.2, that's equivalent to 20 over 12, and then you can just reduce it normally. So everything here I can divide by 4, and that gives me 5 over 3. Okay? Little mental math note there. Now the last part, the last whole section, is on similar solids. And the main takeaway from this was actually something, if you'll remember, was in a homework assignment that we did a long time ago. And I made sure to go over the homework question that kind of referenced this on the sideboard in both of the sections. Okay? So if two similar solids are in a ratio A to B, okay, then two things are true, okay? Their surface areas have a ratio A squared to B squared, and their volumes have a ratio A cubed to B cubed. So if you can find the linear ratio of similar solids, then surface area is two-dimensional, squared. So it's the ratio squared. Volume is three-dimensional, so it's the ratio cubed. So, we'll do one example here. This is a really hard question. A little time consuming. We have this weird shape here for B. And the only unit we have here, we know these things are similar. The only measurement we have is 8. We want to find the surface area and volume of B. So I can do that by finding, first, these are in a ratio of 4 to 8. So the ratio is 4 to 8, which means from A to B is actually in a ratio of 1 to 2. Okay, so the units here are twice as big. So I can find the surface area and volume of B by finding the surface area and volume of A. Now, to find the surface area, this has 1, 2, 3, 4, 5. This has 7 faces. So I need to find the area of all 7 of the faces and add them together to find my surface area. So to find my surface area here, the surface area of A, so I'll do SA. This side is a square, 4 by 4. The bottom is a square, 4 by 4. The side on the left is a square, 4 by 4. So there's 3 of these 4 by 4 squares. I have 2 of these things in the front. So the thing that has the A on it is 2 root 3 in this direction, 4 in this direction. So that's a rectangle, 2 root 3 by 4. So that's going to be 8 root 3. And I have 2 of them. Okay. And then I have 2 of these bases. These, like, this thing in the front. And that, in and of itself, is its own issue. It's a different composite shape. So this is 4, this is 4. This side here is 2 root 3. So this area is a square minus a triangle. The square is 4 by 4, that's 16. The triangle is 1/2 base times height. The base of the triangle is 4, because this distance across there is 4. The height we don't know, so I can try to find it by drawing it in. It's a isosceles triangle, which means that the altitude is also a median. So this little piece over here is 2. So this height, h, I should be able to get from the Pythagorean theorem. So I have 2 squared plus h squared equals 2 root 3 squared. So this is 4. This is 12. So we have h squared equals 8. So h is square root of 8, which is 2 root 2. So the area of this little piece here is 16 minus 4 root 2. So I have that one in the front and that one in the back. So I have 2 of them. So I have 2, 16 minus 4 root 2. So this ends up being, this is 32, this is 48, so this is 80 plus 16 root 3 minus 8 root 2. Okay, that exact answer is 3 different terms. That's kind of annoying. So let's just approximate this. This comes out to be about 96.4 square meters. Okay. Luckily, volume, even though it's a higher dimension, volume is actually a lot easier than surface area. We have to find a volume of a prism. This is a weird 1, 2, 3, 4, 5 pentagonal prism, where this thing that I started to shade in here in pink is the base. So the volume is literally just the base times the height. We just found the surface area of the base. That's 16 minus 4 root 2. The height is 4. That's the distance between the bases. And this comes out to be about 41.373. Okay, so those are the volume and surface area of shape A. So if I want the surface area and volume of shape B, and I know that they're in this ratio of 1 to 2, I know that A squared to B squared is the ratio of the surface areas. And I know that A cubed to B cubed is the ratio of the volumes. Okay? So here you have 1 squared over 2 squared. This is 1 over 4. The surface area here is 96.4. This is the surface area of B. So if I do the cross products here, the surface area of B is about 385.6 square meters. And here, 1 cubed is 1. 2 cubed is 8. And so the small volume is 41.373. So the volume of B is about 330.98 meters cubed. Okay? All right. Well done, guys. I will talk to you later. Good luck.